nice. Hi. Hello, everybody. Hi. So we'll start with our afternoon section. Now I think we are live on YouTube and recording. Everything is set. Well, it seems like people continue coming, but maybe we should start. Yeah, so you can already share your slides. You are now a co-host.
Okay.
Oh, very exciting. Topological order, tensor networks, and subfactors. Wonderful. Looking forward. Okay. So, well, people are still coming, but time is time. Let's start. Thank you very much for, we start with today's afternoon section. The first speaker is Yatsu Kawahigahi. Is from University of Tokyo and Kaburi. Ipmu. And he will talk about topological order, tensor networks, and subfactors. Thank you, Yatsu.
Okay, thank you very much for the introduction. So I thank the organizers for the invitation to speak here. Although I cannot go to Vienna this time, unfortunately, I'm still happy to give a talk here today. So today I'd like to talk about topological order, which means really two-dimensional topological order. And
I'm just sorry, like before, I'm pretty sure very soon people are going to ask you, can you share the slides?
PDF
file.
Is
it convenient to do this? Yeah, it is.
How can I do this? Actually, I'm not so sure.
I think you just throw a PDF into the chat. You open the chat and take your PDF and drag it in there and paste in the chat.
Wait. Okay. So. Okay, it's there now.
Thank you very much.
Okay. Okay. Okay, I'd like to talk about the two-dimensional topological order and tensor networks. You know this well. And then subfactors. So this is an object in theory of operator algebra initiated by von Jones in the 80s. And this was a source of the famous Jones polynomial for quantum invariant in three-dimensional topology. So I'd like to give some kind of interpretation of some results or some works done in the context of topological order and tensor networks from a viewpoint of operator algebras and subfactors. So the structure of my talk is as follows. So I'd like to give some explanation of two-dimensional topological order in terms of gapped Hamiltonians and their ground states. And their ground states are described with matrix product states, MPS, and projected entangled pair states, PEPs. And they are caught much attention recently. And so we have already seen them in many talks here. Then in this talk, we'd like to study tensor networks arising from subfactor theory of Jones in operator algebras. And we want to clarify the roles of higher relative commitance, which is an important notion in subfactor theory. And we'd like to connect these to other topics. So the outline of my talk today that follows. So I first explain very briefly the gapped Hamiltonian and MPS and PEPs. They already appeared in many talks this week. And then our main object is a recent paper of Bulletink and others. And I briefly make some explanation of their work. Then I start to explain some basic notions in subfactor theory, because I think I am the only speaker in operator algebra here, so in subfactor theory. So I'd like to give some basic explanation in subfactor theory, and particularly the notion of so-called biunitary connections on finite graph. Then I'll explain MPO, matrix product operator, tube algebra, which already appeared in some talks yesterday, and the modular tensor category. Then so I will explain some PMPO, projector matrix product operator, and PEPs. And then finally, I'd like to relate this PMPO to a higher relative competence of a subfactor in terms of biunitary connections. So this is what I'd like to explain today. So I make some very brief explanation of gapped Hamiltonian MPS and PEPs. Then from a viewpoint of operator algebras, so there are many aspects of these notions, but I'd like to explain these from a viewpoint of operator algebra. Then gapped Hamiltonians are studied in the context of infinite tensor product of matrix algebras, MDC, D by D, complex matrices. Then that gapped Hamiltonian in this setting is a sequence of self-adjoint matrices in finite tensor products, and they have a fixed gap between the lowest eigenvalues and the next lowest eigenvalues. Then there are many papers studying this kind of notions from various functional analytic studies. So to handle this kind of infinite tensor product at a certain limit of finite tensor powers of matrix algebras. Then a matrix product state, MPS, is a certain expansion of a state in this context using a trace of a matrix product. Then this is useful to explain the ground state of gapped Hamiltonian explicitly for one-dimensional system. This is for one-dimensional lattice. And then we also have a higher dimensional version of this MPS. So this is a projected entangled pair state as PEPs is its higher dimensional analog. And today I'd like to talk about the two-dimensional case that they live on two-dimensional lattice. Then, the next thing is a brief explanation of these 6 authored paper in 2017. So they are considered an algebra of matrix product operators, MPOs, arising from a system of physically nice tensor networks. And such an algebra is called a matrix product operator algebra, MPOA. And they considered a fusion category of matrix product operators and presented a graphical method to construct an interesting system of anyons. So this is a new kind of particles. And then in this way, they get a modular tensor category of anyons. And they discuss some physical consequence of this kind of construction. And they are aware of similarity to an old work of Ogniano in subfactor theory. And first, we give some explanation about the basic observation that their construction is really the same as Ogniano's old work mathematically. Then, so I start with some very basic, well-known setting of subfactor theory. So we are interested in a certain nice infinite dimensional operator algebra, which is called the type 2-1 factor. This was introduced by von Neumann in connection to quantum mechanics and representation theory. Then we consider an inclusion of type 2-1 factors. So n is a 1-to-1 factor, which is contained in another 2-1 factor m. And we simply call it a subfactor. So subfactor means an inclusion of a factor into a larger factor. Then we have a natural notion of the Jones index n of a subfactor. So this is analogous to the index of a subgroup. So this is an index of a subalgebra in a large algebra. So this is somehow analogous to the index of a subgroup in a larger group. And also it's analogous to the degree of an extension of a field. So we have two fields and one field is contained in another. And we have a notion of degree of extension. So this is a kind of index. And we have an operator algebra version of this index that's called the Jones index. And then in the case of the index of a subgroup or the degree of extension, we always get an integer value or possibly infinity. But now we can get non-integral values for this Jones index. And the initial surprising discovery of Jones was that the set of possible Jones index values is this set. So below 4, we have discrete series converging to 4 times cosine squared pi over n, and n starts with 3, 4, 5, and so on. So for n equals 3, this value is 1. The next value is 2. The next value is something between 2 and 3. The next value is 3. And after 3, we get a series of values converging to 4. Then after 4, we have continuous values. So everything is possible up to including infinity. Then the square root of this Jones index value is similar to the quantum dimension for representation of a quantum group, or also the statistical dimension for super selection sector in quantum field theory. So this is a kind of dimension in this setting. Then we have fusion categories of bimodules for this setting. So suppose we have a subfactor n in M with finite Jones index. So the index could be infinity, but we are interested in the case where we have finite index value. Then we set this smaller factor to be M0, and we set the next one, M, to be M1. Then we can repeat this kind of construct, extend this inclusion so that we get a series of inclusions of two-one factors, M0 containing M1, M1 containing M2, and M2 containing M3. So we have this infinite increasing sequence of operator algebras. This is called the Jones basic construction. Then using these algebras, we can consider...
There are now type 2 or they still stay in type 2 or type 2-1 or
type 2-1, yes.
Okay.
All are type 2-1 factors, yes.
Okay. Yeah. And all these M0 and M1, they realize all the type 2-1, like what you realize all the Jones index values, or...
Yeah, so we can take a subfactor with an arbitrary finite Jones index value.
Right. Yeah, I'm just saying that. So these M0, M1, M2, they sort of realize all these index value, like for cosine pi over n squared.
I mean, for any values for, say, 4 cosine squared pi over n, we can choose a M0, M1. Then the next index value of M1 in M2 is the same as the original index value. So for this repeating basic construction, the index value is preserved.
Okay, so it's very good.
Okay. Yeah. Then we can consider 4 kinds of bimodules. So we take some algebra MK. Then this is a bimodule over the initial algebra N or M. And we have the left action of N and M. And we also have the right actions of N and M. So we have 4 kinds of bimodules: NN bimodules, NM bimodules, MN bimodules, and MM bimodules for all K. And then we have a natural notion of irreducible decomposition of bimodules. Then we have infinitely many algebras, and we have 4 kinds of bimodules for each MK. Then if we make irreducible decompositions generically, we would get countably many mutually inequivalent bimodules. But in some nice situations, we have only finitely many irreducible bimodules arriving in this way. Then in this situation, we say that the subfactor is of finite depth. So this is the kind of finiteness assumption for something like a representation category. And for some historic reason, we say depth. And this condition is analogous to rationality of a conformal field theory. So this is also finiteness of a representation theory. And also we have similar rationality for quantum groups. And then in this way, we get finitely many irreducible objects, and we have a natural notion of tensor product. So in this way, we get a fusion category of, say, n bimodules. And also we have a fusion category of m bimodules. Then we have another notion of a commuting square, which is important for this talk. So we fix a subfactor n in M with finite joint index, and we assume we have a finite depth condition. Then we look at this inclusion of 4 algebras. So the initial algebra is M prime intersection with MK, and this prime notation means the commutant, the relative commutant. So this is an algebra of all the elements in MK, which commutes with everything is in M. So M prime in MK is something which is in MK, which contains, which commutes with M. And then we have the relative commutant of M in MK plus 1, and also we have the relative commutant of N in MK, and we have the relative commutant of N in MK plus 1, and also we have infinitely many values of K. And then we look at these 4 algebras. So this is a square of actually finite dimensional C-star algebras, just a direct sum of matrix, full matrix algebras. And then such a square of 4 algebras satisfies some nice special property for the commuting square property. And if n or m has a nice approximation property with finite dimensional subalgebras, then actually this above commuting square for a fixed single sufficiently large K has complete information to recover the original infinite dimensional algebras. So for fixed K, this diagram just means that we have 4 algebras, 4 finite dimensional algebras, but these finite dimensional algebras have complete information to recover the original infinite dimensional algebras. This is a deep theorem of Thorin-Popper. And then classification of subfactors is reduced to the classification of certain commuting squares of finite dimensional C-star algebras. So in this way, we get some finite dimensional algebras. Then in order to describe these inclusions of finite dimensional algebras, we have the next notion. So we have the conversely, suppose that we have a commuting square of finite dimensional C-star algebras, A in B, A in C, and B and C are in D. So this is an inclusion of mutual inclusion of 4 algebras, A in B, B in D, A in C, and C in D. Then still we can apply the joint basic construction for these 4 algebras, finite dimensional algebras. Then we can extend the inclusions horizontally and also vertically. And then in this way, we get a double sequence of finite dimensional C-star algebras. So we have A, the initial one to be A00, the next one B is A01, the C is A10, and D is A11. Then we can extend this to the double sequence, AKL of finite dimensional algebras. Then for increasing K, we have a large algebra, and also for increasing L, we have a large algebra. So we have double sequence of finite dimensional algebras, and they are increasing in 2 directions. Then we can take a limit algebra. So we have 2 subfactors. Actually, in this way, we get a subfactor. So A0 infinity. So A0 infinity including A1 infinity. So this is an inclusion of infinite dimensional algebras, and actually there are 2 1-factors. And also we have, so this comes from horizontal limit, and this is a vertical limit for A infinity 0 containing A infinity 1. So we have 2 limiting procedures for this double sequence. And in this way, we get 2 subfactors arising from the initial data of finite dimensional C-star algebras. And then so this is from the arbitrary finite dimensional C-star algebras. But if the original commuting square arises from a subfactor, then we get back basically the original subfactor, or n in m, or also anti-isomorphic to n in m. But so basically, so we get two subfactors, but both are essentially the initial subfactor. But more generally, we can we can apply this construction from arbitrary finite dimensional C-star algebra, or commuting squares for finite dimensional algebras. Then, in order to describe this situation, we have a natural notion of biunitary connections. So for an inclusion of two finite dimensional C-star algebras, A and B, we draw the Brattelli diagram as follows. This is one typical example of a Brattelli diagram. So A and B are both finite dimensional C-star algebras, which means that they are direct sums of matrix algebra. So for suppose A has three direct summands, irreducible summands. We have matrix algebra, another matrix algebra, and another matrix algebra. Then for B, we have again three irreducible components. So we have one matrix algebra, another matrix algebra, another matrix algebra. Then for edges, it means that the initial matrix algebra contained in another this first matrix algebra of B with multiplicity 1. So here actually all the edges are single, but we could have multiplicity. So here we have the second algebra, matrix algebra. So this is included in the first component and also the second component and also the third component, all with multiplicity 1. So this is our inclusion of finite dimensional matrix algebra into three pieces. And also this last piece is contained only in the last piece with multiplicity 1. So this is a Brattelli diagram. Then for inclusion of A and B, we have this kind of graph, finite graph. Then here we have algebra A here, and B here, and C here, and D here. Then for an inclusion of A in B, we have a Brattelli diagram, just like this here. And we have another Brattelli diagram here, another Brattelli diagram here, another Brattelli diagram here. Then, so we have four finite graphs arising from a commuting square. Then we choose one edge here and this edge, and one edge here, and one edge from this diagram here, and one edge from this diagram here. Then we connect these four edges to make a square. Then it turns out that for each such a square, we get a complex value for attached to a square. So this is an assignment of a complex value, complex number to each square arising from a four Brattelli diagram. So this is a kind of lattice model. We have a notion of solvable lattice models, and in this way we get a square from a graph, then we get a complex number, possibly with a spectral parameter. So this is a similar situation to that. Then, so this is, we get a complex number from four edges, and then we have to satisfy some unitarity condition in two ways. So this means they are doubly unitary. So we have a biunitary, and we have a name connection, which comes from an analogy to a discrete version of differential geometry. This kind of biunitary notion was considered by Oknian and Hagerup many years ago, almost more than 30 years ago. Then, so we can construct two subfactors, A0 infinity and A1 infinity, and the other one, A infinity 0 and A infinity 1, rising from a commuting square, which is given by a biunitary connection. So if we have a finite depth for one subfactor, then we also have the finite depth for the other subfactor. This is known due to Sato. Then so from now on, we assume that this finite depth condition holds. Then we would like to define a 4 tensor. So this is so everything was well known in subfactor theory for almost 30 years. But then we would like to pass from this setting to a setting of 4 tensor in the work of Bulletin and others. And then for if we have biunitary connection, we get a complex number for a choice of 4 edges. So we have 4 index set, and if we choose one from these sets, we get a number. So this is basically the same as 4 tensor. So we have 4 index sets, and we choose 4 labels from them, then we get a complex number. So this is just a rewriting of this biunitary connection. So in this way, we get the 4 tensor. But then this setting is slightly different from the usual setting of 4 tensor appearing in this kind of topological order, because we would like to connect 4 tensor horizontally and vertically. But now in the previous setting, we have 4 Brattley diagrams, which could be all different in general setting. Then so we cannot compose 4 tensors, but for just for resolving this issue, we have the horizontal and vertical basic construction. Then we use this kind of 2-step inclusion. So instead of AKL in AK plus 1, we use AK plus 2 and L. Then we have this doubly expanded commuting square. Then we get a natural corresponding notion of 4 tensor, which can be applied to this setting. Then from this kind of biunitary connection, we can get a fusion category, and we also get a 4 tensor. So we have natural notions of a tensor product and the reducibility compositions for such a biunitary connection. So okay, we can compose biunitary connections, and also we can make reducible decompositions of biunitary connections, just similarly to these notions for bimodules. Then we have a fusion category of biunitary connection, and this is really an equivalent fusion category to the fusion category of bimodules. And this is a classical work of Saida-Hagerup. Then we label each biunitary connection. So we actually, through this kind of tensor product and irreducible decomposition, we get finite family of irreducible biunitary connections corresponding to finitely many objects in the fusion category. Then we label them so A, B, C. So this is label A. This is also label A. Then we can define 4 tensor from connection this way. So just basically, so we have a label I, J, K, L for edges, and we use the same labeling I, J, K, L. So this complex number is basically the complex number arising from the connection, but we have some this kind of normalizing constant, but this is just for convention, so this constant is not essential. Then from this kind of 4 tensors, we can construct a matrix product operator and also a projector matrix product operator. So just so we draw some circle, and here, so this is now actually, so for this crossing of 4 edges, we have 1 tensor. So in this picture, we have 1 tensor here, another tensor here, another tensor here, another tensor here. So we have 4 tensors. So on the circle of length 4, this so length means the number of tensors.
So the point is the tensor and the
yeah. So this crossing is a tensor.
Red thing is the module, or what? The red.
No, the red thing is yeah, corresponding to a bimodule, but here this is just a label for this index set. So we have 4 indexes, but two of them are same. So we have 2 index sets. So here we have 1 index set for this tensor. Here we have the same index set for this tensor. And here, and this index set is common for all A. But here we have 1 index set here, and we have the same index set here. And this index set depends on A, on the choice of A. So we need some label for this part, because we have different index sets for different labels here for this red part.
I thought this blue thing, this index set comes from the picture before. You have I, J, K, L. That is the blue thing, right? And they on both ends they have the same I, K, K, J, J, and then yes.
So here the index set for I and the index set for J is the same. We have the same index set, and this is common for all A. But here we have another index set to which K and L belong. So the one index set K and another index set for L. And this index set depends on A. Okay, so we have two different index sets.
And this KL is the red.
Yeah, this now in the next picture, K and L are in the red thing. Yeah, for this part is K and L. Okay.
And then you put them together, form them together.
Yeah. Then for this kind of thing, we can compose. So if we have another picture with B, we can move this picture with B label to the inside of this picture. In this way, we can define the composition of these two pictures, and this define the fusion product. So in this way, in this way we can define fusion product, and this is a matrix product operator.
Four things.
Yeah, the number is fixed now. And actually this makes sense for any number. So this 4 can be say 3, 6, 7 or anything. But the number 4 is important for the PEPs which appeared later. Then so here in this picture, we now have no labels for A. And this is actually a summation of A with some normalizing coefficient. So this is a quantum dimension, and this is a kind of global dimension, the square sum of the dimension, quantum dimension, and summation over all possible A. So this is if we drop the label A, so just blue and red picture, so this is a summation over all A. And then it turns out that this is now a projection with respect to the with respect to the multiplication of this matrix product operator. So in this way, we can define a projection, PMPO. So then this product structure of these MPO is isomorphic to that of the relative tensor products of bimodules, also connection, biunitary connections. And then we have the so-called zipper condition, which appeared in the paper of Bultink and others. And then so we can interpret this zipper condition in terms of biunitary connections. Then we have the same product structure also for this picture. Then some Bultink and others, they defined the Enyon algebra for this setting. So they introduced an Enyon algebra for 4 tensors. Again, this number 4 can be arbitrary, but we just choose 4 this picture. Then they obtained the modular tensor category describing anyons in their topological order. So now we have 4 crossing like this one, blue and red. And here we have some this new tensor arising from the zipper condition. Then we have this picture represents a typical element in the new algebra, the Enyon algebra. And so if we have 2 pictures of this type, then we can put one into the inside here of the other, and this gives a product structure. Then in this way, we get finite dimensional thin-star algebra. So again, it's a direct sum of matrix algebras, and we are interested in each simple summand. And then each simple summand is given by this kind of picture. So we have new tensor here. And this gives an Enyon in this system. So the new irreducible object in the new tensor category, which is braided now. So then this Enyon algebra, they actually are isomorphic to the Okniano's tube algebra, which appeared in the talks yesterday for the fusion category of bimodules arising from subfactor. So in particular, the modular tensor categories arising from this is identical to the one known in subfactor theory. in the asymptotic inclusion, or also the Longo-Rayleigh subfactor. And also we get the Ferrarinde formula, which gives the new fusion rules in this quantum double tensor category. So this is a description of the Drinfeld center, which is well known. Then, okay. Then, now I'd like to explain our subfactor interpretation of PEPs in this context. So we would like to describe a PEPs arising from a biunitary connection. So for this projection, a projector matrix product operator of the length 4, this picture. So this is a projection. And then we have four exterior wires here. And also we have 4 internal wires. But then we can consider, so we can combine these 4 internal wires, just combine, we can just combine them into one. Then we can regard this having 4 external wires and 1 internal wire. Then we can regard this as a 5 tensor. So 4 external labeling and 1 internal labeling. So we get we get the 5 tensor from this picture. So now this number 4 is important and it is fixed. And then we can put this picture so on the lattice, so in this way, so in this extension, we have a square lattice of size 2 by 2. So here we have, this is a lattice, so one wire here, one here, and another here, another here. So we have 2 by 2 square lattice. Then for each crossing of the square, we put this picture. So this picture is here, one picture is here, another picture is here, and another is here, and another here. But then here we connect this edge and this edge. So we connect this part, and also we have connect this part, and we have connect this part. Then in this way, we get some things. Then so we regard each the 5 tensor. So we have now connected this part. So we have one internal wire here, and another internal wire here, another here, another here. We have these 4 internal wires, and we have 1, 2, 3, 4, 5, 6, 7, 8. We have now 8 internal wires. And then this picture can be regarded as a picture represent some state, some vector. And because if we fix these, so this is an open wire, but if we put some label here, so we put everything here, so 8 internal wires and 4 internal, sorry, 8 external wires and 4 internal labels, and then we get the complex number. Then just like the case of the matrix product state, we can regard, we can interpret this picture as a state. So for here, if you have I, j, k, l, and so on, then the number given by this picture is a coefficient for basis vector labeled by I, j, k, l, and so on. So this picture represents some state, and so this, and then this is a particular case of a PEPs. So this gives a PEPs on the square lattice, and in this picture, and then and this can be done on any square lattice of n times m. And so this, in this extension, n is 2 and m is 2, but we can extend this to any extension. And then, so this is PEPs. So this is a vector in some finite dimensional Hilbert space. So actually, this gives a ground state of some local Hamiltonian arising from this tensor. So this is a well-known standard construction of a PEPs in this particular situation. Then,
so in this PEPs representation, it's also include a chiral topological order or only non-chiral topological order?
This is, I think, non-chiral one, I think.
Non-chiral, I see.
Yeah. Yeah. Then, so PEPs and PMPO. So in this, the previous picture, so So for the PEPs in the right figure in the previous slide, so we have so this we have PMPO of okay, the previous picture is this one. Then we have now a larger red circle, which covers everything, just like this. And so we have a large red square, I mean circle, just outside of the previous picture, this one. Then so this is now a PMPO, projectile matrix product operator of length 8, because we have now 8 crossing on the circle. So this acts from the exterior wires, and then actually this has no effect. So this picture represents the product of the previous state and this new matrix, but this projection has no effect. I mean, we can just remove this exterior red circle. It means that the PEPs is contained in the support of the projection, this PMPO of length 8. Then, so yes, so it means that this PEPs leaves the intersection of the range of PMPO also. Okay, this is a PMPO picture. So this is one PMPO which acts on the PEPs from the outside. And also we have here, we can also put another PMPO with length 4. We can apply this PMPO from the inside here, and another matrix here, the inside. And also we have another PMPO here and another one here, each having length 4. So for these PEPs, we have an action of 5 PMPOs, 1 from the outside, 4 from the inside. Then, but each action of the projection has no effect on this PEP. So it means that the PEPs leave the intersection of the ranges of these projections. So the range of PMPO of length K, so in this case length 4, and this picture has length 8, and so this can be we can consider any possible values of K, actually larger than 4 in this case. So the range of this PMPO of length K has a physical some meaning in this setting. So we would like to identify this range of this projection is something important and well studied in subfactor theory. And actually it turns out that the range of this projection is isomorphic to the higher relative competence of a subfactor. This is the next and actually the final thing. So the range of PMPO of length K, actually this can be 1. This K can be any positive integer. And then this is naturally identified with the higher relative commutant for this subfactor. So the commutant with A infinity 0 in the algebra A infinity K. So we have the 0 and K. So the commutant of the first one in the case one. So this is a relative commutant. So this gives a finite dimensional algebra. So this is a higher relative commutant for subfactor A infinity 0 containing A infinity 1. Then actually, so we can prove this because an element in this range, this picture, so this state is identified with the front field of string. So we can take any element in the range of this projection. Then we can, in the original picture using the Brattley diagram, we can get this kind of connection of edges, and we can, so we have a closed path of edges here. So we have here we have 4 tensors. So it means that now we have 8 edges from the original Brattley diagram. Then we call a string such a path of 8 edges because we have a closed path of edges. Then we can take, say, this one to be the initial vertex, and this one to be the end vertex. Then we can draw this kind of string. So we have one path of length 4 from this initial vertex to this final vertex. And also we have another path from the same initial vertex to the same final vertex. So this is a string of edges. Then so we have a lot of such strings arising from this state. And then we can identify such strings with flat fields of strings. So this is a notion of opinion in subfactor theory. So in this way, if we take any state in the projection, we can get such an element, and also we can make a converse correspondence. So we can make an identification of this state in the projection range with the flat field of strings. And then note that this is one subfactor of the two arising from the basic construction. And actually, for the quantum double construction, the Drinfeld center construction, we used this subfactor. But here we have the other subfactor for this higher relative commutant. So we have two subfactors, and so they both naturally appear in this setting. And it's known that these two subfactors are kind of complex conjugate Morita equivalent. So we have a natural notion of Morita equivalent for subfactors, and we have two subfactors, and they are basically Morita equivalent. But for one, we have to take complex conjugate of 6J symbols. So we have to put a complex conjugate here. But basically, we have two subfactors which are mutually Morita equivalent, and one subfactor appears in the Drinfeld center construction for the Enyon algebra, and the other subfactor appears in the higher relative commutant arising from this projection range. So in this way, two subfactors play natural roles in this context. Okay, I stop here. Thank you very much.
Thank you very much for your talk. Is there a short question?
Can I have a short question? Yeah. So so in this construction, can you also generalize it for Fermat system?
I don't know yet. I think it's possible, but I haven't seriously thought about this yet.
Okay, thanks.
Yeah. Otherwise, as we know before, like we still have a lot of time to discuss in more details with the speaker in the breakout section afterwards. And today, Yatsu, you will have the second breakout room. It's just because the first breakout room is today gone. It's for technical reasons gone. So you will have a second then with the order 3, 4, 2, 3, 4 are available today. Okay. So our next talk begins at 3 o'clock European time. And from now on, I just leave the section over here. If you want to still ask questions and discuss, feel free.
Okay, thank you.
You're welcome. Thank you for your talk. It has been a long time. I just recently began to come back to the subfactor thing. It's been a long time. Yeah. And yeah, I came back because of the two group representation thing, because I think somehow these subfactors should also. Oh, thank you. Okay. Yeah, now we know the tricks now. Like, yeah, you won't just have to draw the files over there. So these subfactors, this fusion category has to also to do with positive energy representation of loop groups.
Right? Yes, yeah. That's another thing.
I think we even discussed this when you were here.
Yeah.
then I didn't use this. Then I totally forgot. Then my professor was asking, like, I think because for loop groups we also have other sort of representation, and the reason why we concentrate on positive energy representation, the rotation S1 will have positive eigenvalues. Is it because only those positive ones can be connected to the subfactor theory?
Yeah, right. So that's the direction of conformal field theory, and then from positivity of energy, we need positivity of the representation, and then in this way we can get a fusion category of representation of a chiral conformal field theory.
So yeah, fusion category. Exactly. So it's also very nice. It's also very nice that then people realize this. Am I correct? I understand these works are pretty recent. People realize this fusion category also is the fusion category that the top which show up in topological orders. Is that okay? So they're exactly the same, and well by and I assume it's not like 2 plus 1, or is it 2 plus 1?
Yeah, 2 plus 1.
Or 1 plus 1. It's 2 plus 1.
2 plus 1.
What? 2 plus 1.
Yes.
Excuse me, I have a question. So this operator algebra arises in the subfactor theory. Is there any relation to the so-called E1 algebra, E2 algebra? You know, in some extended
actually, I don't know. Yeah.
I see.
I'm sorry, I don't know. Actually, I'd like to know, but I don't know.
I see, because that also some kind of operator algebra appear in the higher category. Then we go to so basically the question is that whether this subfactor theory can be generalized to higher dimension.
Okay.
And then whether there's something related to the E1, E2, E3, or things like that. Okay.
Gang, I don't think that the current work on like EN algebras kind of has connected yet with like operators really.
Okay.
The closest that I'm aware of is Chris Douglas and Andre Enriquez might have some stuff on kind of a version of non-unital E2 algebra that's in a kind of von Neumann algebra world.
I see.
Right. Reason that they construct this, what is it called? Conformal nets.
Yeah, conformal nets. That operator
category or some.
Conformal net. Operator. Yeah, conformal net is an operator algebraic realization of a chiral conformal field theory.
Right, and chiral conformal field theories. I mean, vertex algebras, chiral algebras are in the same world as E2 algebras.
Okay.
In that sense,
but,
right?
But also, I mean, like the fact that it's kind of in vertex algebra, you think it has holomorphic dependence, but there is a sort of thing that I know that they extract from conformal net, which is really quite topological, but it's not unital, and so a lot of the techniques that you might want to use, that you might think you can use, that are really topological things, require that there be a unit. So.
I see. Okay, yeah, that seems also a big field to enter.
Okay. Okay. Now it's slowly the time, and we are. I guess everyone has already the file for the next talk. The next talk will be given by Jürgen Fuchs. He will talk about PEPs and by categories. PEPs. And I guess you sort of realize maybe Yatsu is not the only one talk about some operators. Okay. Thank you.
Okay, thank you very much for the invitation to give a talk. So I will talk about PEPs, which already appeared in Yasu's talk. In a bit more detail, what I want to do is to understand MPO symmetries. They also appeared to some extent in Yasu's talk for the case of PEPs, describing ground states of stringnet models through topological field theory. And there are various motivations for doing that. If you have a PEPs describing stringnets, then there are situations where you want to allow for boundaries. And this has various applications, for example, for some aspects of error correcting codes. And another important area is the relation to conformal field theory. There has been introduced something called a strange correlator, which allows you to understand various aspects of conformal field theories directly on the lattice. And there are many more, but I don't want to talk about these motivations in any detail. What I will do is start with a short reminder about PEPs and MPO, partly repeating what Yasu has already explained. Then I will tell you how to get from MPO symmetries to fusion categories and bimodule categories. And then in particular, in a particular case, the situation where the bimodule category is invertible, describe certain two-Morita contexts in fusion categories. And this will be the first half of the talk. And in the second half, I will try to explain how these results can be understood in terms of state sum topological field theories. And all of this is work in progress together with these four people here. So matrix product states first, they do not appear in the title, but I want to start with them in order to get a explanation of why we talk about PEPs. The MPS case is the one-dimensional case. And if you have a gapped Hamiltonian for one-dimensional lattice with periodic boundary conditions and translational invariance, then we can define certain states which are an efficient approximation for the ground states of those systems as an element of the state space, which is a tensor product of state spaces for each site. And this is given by such a formula here, where the input is a certain rank 3 tensor, where two legs have dimension d, that's called the virtual dimension, and a third leg has dimension small d, that's the dimension of this physical space that we have at each side. And the AJ that appear here in this formula are just the capital D by capital D matrices, which I get when J has a fixed value. And diagrammatically, a picture that certainly many of you have already seen, this is expressed by such a picture here. Let me mention the so-called fundamental theorem of MPS. It will not be directly important, but something similar will play a certain role. We call an MPS injective if the matrices AJ for all values of J upon linear combination and forming products give you the full D square dimensional matrix algebra. And then the fundamental theory of MPS states that you have two such injective MPS based on an MPS tensor A and an MPS tensor B. Then the two states that I get are equal if and only if the matrices A and B are related by conjugation by a matrix X up to possibly a phase. Now, let me also mention a different description of these MPS, namely we can take at each side two d-dimensional degrees of freedom that's indicated here. Then we maximally entangle pairs on neighboring sides, which I indicate by this picture. And then I map these degrees of freedom that I have here to the physical space that corresponds to my matrix A. And this is indicated by this picture. The only reason I'm showing this is to show you that an MPS matrix product state can be realized in this way. And that is what one would call a projected entangled pair state, because we have entangled pairs here and then we deal with those. Now, projected entangled pair states is abbreviated by PEPS, and PEPS is usually used in 2 dimensions. But what I have just shown to you shows that you can already do this in 1 dimension. The virtue of this construction is that it generalizes directly to any dimension. And I will do this in 2 dimensions. That's a value for which the term PEPS usually is reserved. So a picture in 2 dimensions would be as follows. At each side in the 2-dimensional lattice, I have a corresponding picture where I have these entanglements at these sides, and then these lines here correspond to the physical leg of the tensors here. And when I do that, then here I get a PEPS tensor which has 1 physical leg and a certain number n of virtual legs. In the picture, it's 4. That's actually the same type of picture that appeared in Yasu's talk, and I will abbreviate this by pictures like this here. But what I will, when I will do concrete calculations, I will instead not work with a square lattice, but with a hexagonal lattice, so that this number n of virtual legs is equal to 3. Then we need matrix product operators, and these have been introduced in the connection of with the observation that to describe the properties of PEPS wave functions that describe ground state of string net models, then you have to deal with certain symmetries of this PEPS tensor A, and those symmetries you can realize through what is called the matrix product operator, which I denote by B hat here. And this is obtained as follows. I will not go into detail. Here are some references, which partly also were mentioned by Yasu in his talk. The operator is associated to some kind of defect line in my lattice, and it is local in the sense that it consists of various tensors, which I call B here, which now have 4 legs, 2 internal legs, which are drawn in red, and 2 external legs. And then my operator B hat is defined here in a similar way as a trace as we have defined MPS, where now the external legs are contracted with the virtual legs of the PEPS tensors. So that means in the summations here we have a capital D. Now the reason that these objects are called MPOs is actually kind of historical, because a different possibility is not to take the external dimension to be the virtual dimension of the PEPS, but rather the physical dimension of an MPO, and then of an MPS, and then you can use the MPO as an operator acting on the MPS. Well, that is the setting that I'm considering. And now let's see how this is related to various types of categories. And I start with a tentative description of MPOs in connection to fusion categories. I will use the following abbreviated notation. So this small disk here would be my MPO tensor B, and I just indicate the two types of legs now in this way. And also I'm looking at a whole family of MPO tensors labeled by some index A. The same label, labeling actually that Yasu has been using. And now you can observe that if you have two of the corresponding operators, then by just concatenating the external legs of the corresponding tensors at each side, you can fuse any two of these MPOs. Now, by invoking an analog of the fundamental theorem of MPS, that's called the fundamental theorem of MPO, you can argue that actually the fusion of such two operators can be written as a linear combination. And that means there's a corresponding fusion tensor, which I indicate by this picture here. Now, one possible interpretation is...
for in Yatsu's talk, he has like 4 external leg and 1 internal leg. Is it like?
Well, we will. Maybe I should not go into that now. Maybe we can see it later. Let me continue here. So there is one possibility to say, well, this just describes a tensor product in a fusion category, where the label A corresponds to isomorphism classes of simple objects. And then the associativity of the fusion would be encoded into the 6J symbols of the category C, which I denote by a 0F here. The reason for this additional label will become clear soon. And we would just say that the two possible ways of fusing that I describe here and here are described by are related by the 6J symbol. But there is a more general interpretation, let me to say, well, this is just a tensor with certain labels, which I don't want to identify in detail, and they correspond to, well, they have to satisfy a recoupling identity in which the 6J symbol of this fusion category C appears. Now, what I precisely mean by MPO representation here will have to be explained, and I will not explain it right away, but rather have a look at the PEPs first. For that, I look at the concrete PEPs description of ground states of string net models that has been considered in the literature, except that I allow for arbitrary fusion categories, so arbitrary fusion multiplicities in particular. So the formulas will look a little bit more, will have more labels on them. So doing that, if you look what that means, is that the PEPs tensor that I have described so far, this has 3 virtual legs and a physical leg, which is not shown here. That really corresponds to this situation here. This is often called the triple line notation. It just says that I have additional labels and at the ends here I have a multiplicity which is the possible values for this are fixed by this triple of labels that I have here. And at this point, this is just a description which you can use in various ways. And then, of course, you should ask what have all these labels, how can I explain their presence? And one possibility, again, is to say that I have a fusion category. I call it now D. It's a different one from the one I have talking about before, so the different name here, where all these labels that I have here are just, again, labels for simple objects, and then the multiplicities are just correspond to basis choices in corresponding morphism spaces. So if I have A, alpha, C here at this vertex, then this corresponds to the tensor product to the space of morphisms from A tensor alpha to C, and analogously for the other ones. And then the middle label K, which corresponds to the physical leg, which is sticking out of the screen, that would again be of the same type. But again, this is only one possible interpretation. A more general interpretation, in this case, the Pep's tensor would be nothing but the ordinary 6J symbol of this category D. But again, there is a different interpretation. Namely, you can say that you have this fusion category, but only the labels alpha, beta, gamma correspond to simple objects of the fusion category. And then there is something else. Let me, for the moment, just call it the Pep's realization, such that I have this identity with the 6J symbol of the fusion category D appearing as a recoupling identity for the Pep's tensor, in the same way as I had an identity, a recoupling identity for the MPO fusion tensor before. Now, what is a sensible mathematical interpretation of that? Well, it's that actually I'm describing a situation where I have a module category. So the labels alpha, beta, gamma here will be correspond to simple objects of a fusion category, and the other labels capital A, B, C will describe simple objects of a right D module category M over a fusion category. So the module category over monoidal category is just the higher analog of module over a ring. So just like in a ring, you can act with an element multiply an element to of the ring to an element of the module. Now you can act with an element of your fusion category on an with an object of your fusion category to an object of your module category. And I have described this action here by a little triangle, and it's an action from the right. Just that's a choice we decide to make here, and there are actually various orientation choices which are implicit, which I do not show here. Now, in this description, the recoupling identity for the Pep's tensor just tells you that the Pep's tensor is what is called a module 6J symbol. And that's the following. It just like the 6J symbol expresses the isomorphism between two tensor products with double tensor products with different bracketing. Now the 6J symbol, which I call module 6J symbols, expresses an isomorphism where we act on an object of the module category, first with alpha and then with beta, and compare this to the action of the tensor product of alpha with beta. Or in pictures, this would be the description of this 6J symbol. And just for having things completely explicit, I have written here the corresponding this pentagon identity that is given by this recoupling identity before. And of course, you should not look at all the details here. It's just maybe you should remember you have three on the left and 3, 3, 4 on the right. So that's why the F symbol for F, which is the ordinary 6J symbol of the fusion category D, appears in that recoupling identity. And this is nothing but the mixed pentagon identity that states the equality of two distinguished isomorphisms between this object here and this object here, in the same way as the ordinary pentagon identity states the equality of two distinguished isomorphisms between two triple tensor products in a fusion category. So this gives us an interpretation of PEPS tensors. Now let's go back to the MPO tensors. Recall we had this recoupling identity for the MPO fusion tensor. In this situation where we describe stringnet models, the fusion tensor again looks more explicitly like here, where I have this triple line notation, simply meaning that these various multiplicity labels that we have here are determined by the triple of these labels. And the interpretation now of the recoupling identity, was very similar to the one that we have for the PEPS tensor. So again, it tells us that we deal with a module category, but we want to have the same underlying category, and now there should be an action also on the fusion category C, and this will be from the left. And then the MPO fusion tensor is precisely of the same type as the PEPS tensor, except that now we deal with the left action of the fusion category C. So the picture is like that, and the module, the corresponding module 6J symbol, which I now call 1F, describes the isomorphism of acting with the tensor product from the left or acting twice from the left. And again, if you write out the recoupling identity, you see that it's just a mixed pentagon identity stating an equality of the two distinguished isomorphisms that you get via the 1F and 0F symbols between the object that we have here and the object that we have here. Well, the next step is to realize that we are still lacking the MPO tensor. And the MPO tensor now, Chen Chang, maybe that's where what your question referred to. Here we have these 4 legs, and in the stringnet situation, again explicitly these legs actually correspond to such triple labels, and the full expression is given here. And what we have not yet used is that the MPO tensor satisfies further consistency conditions. First of all, the zipper condition that's already has been mentioned by in Yas's talk. So remember, the fusion tensor tells you how to fuse different MPOs, but we do that by doing it locally on the lattice. But where precisely we do that on the lattice should not matter, and therefore we have an identity which in the simplified notation looks like this. And there is another condition called the pulling through condition, which comes from the fact that the MPOs, these are, I have called them to correspond to defect lines, and those lines I can move freely through the lattice of PEPT tensors. And actually that's what one requires, and this is actually related to a renormalization group transformation for MPOs that are required to be scale invariant. So we have these two additional conditions. And again, this has an interpretation in terms of categories, namely M is not only a right module category over the fusion category D, and simultaneously a left module category over the fusion category C, but these two actions are compatible. So M is a bimodule category. And then correspondingly, there will be a bimodule 6J symbol, just expressing that we have an isomorphism between the situation where we first act from the right and then from the left, or the other way around. Or in pictures, we have such a relation. This is again analog of the defining picture for ordinary 6J symbols, except that instead of tensor products, now we have a left and a right action to consider here. And I call this bimodule 6J symbol 2F. And then the zipper and pulling through conditions look like this. And again, they are just mixed pentagon identities. So let me summarize this. If we have a situation with a PEPS tensor, MPO tensor, and MPO fusion tensor, and all these consistency relations I have been listing, then these data and conditions amount to having a pair of fusion category C and D and a bimodule category M, which is a left C and right D module category. And I have identifications that the PEPS tensor gives me the module constraint for the right action. The MPO fusion tensor gives me the module constraint for the left action, and the MPO tensor is the bimodule constraint. And also I have corresponding identifications of the various pentagon and mixed pentagon identities. And to summarize this in one sentence, if I have a string net PEPS, which satisfies a recoupling condition described by a fusion category D, and MPO symmetries described by a fusion category C, then this is possible if and only if there is a CD bimodule category such that the constraints for this system are those that I have been describing. We can look at a special case that M is an invertible bimodule category, and then what we get is a two Morita context, or also a two object bi category. So we have a bi category with two objects, which I denote here by a black dot and a white dot, and then the one morphisms of one of them are the fusion category C. The one morphisms of the other one, endomorphisms are the give the fusion category D, and the one morphism categories from one to the other are M and the opposite category M bar. And in this particular situation, D is nothing but what is called the dual of C with respect to M. So this is the category of module endofunctors of M, and also the other way around. And in particular, this implies that the Drinfeld centers of C and of D are equivalent. But I will not go into that, but rather now in the last part of the talk, try to describe how you can get these results from a picture in which we apply a certain topological field theory of state sum type to a suitable manifold. So the data that we have are now, besides our PEPS tensor A and MPO tensor P, some surface sigma for which we choose a cell decomposition, and for concreteness, I take this decomposition such that it's a honeycomb lattice, so thereby it fits directly to what I have been saying, and then according to what we have seen for the PEPS tensor in this situation, the space that is associated to the physical leg of the tensor A is given by by morphism spaces of this fusion category D. And that I have at each side of my lattice. So to the surface as a whole, I will associate just the tensor product over all vertices of the lattice of these spaces for each side. And of course, this depends on my cell decomposition. But there is a protective space or physical subspace, which I get by looking only at those states where I have contracted all the virtual legs of the PEPS tensors. And you can convince yourself that this does not depend on the cell decomposition. And the goal is now to obtain this protective subspace, more explain it in terms of a derived Vierotides state sum construction. And this construction should be such that these PEPS and MPO bimodule categories, and in the special case, the bicategory that I have described can be inferred from that construction. I should mention that in the, this is completely analogous to what in one dimension, so for MP S has been done already a few years ago, and also there is a description of what is happening in the case that M equals to D, so just D as a bimodule over itself, meaning that also C is equal to D, and if you look at the paper, you will see that you can describe their results as a specialization of what I'm going to describe now. So the strategy is the following. We take a Turaiff-Viro topological field theory. So the input will be some, should be spherical fusion category D. And then the topological field theory is a functor which assigns to a three-manifold linear map from the input, the in boundary to the out boundary. And we look at a particular type of three-manifold where the in boundary is empty. So the corresponding state space are just the complex numbers. And then the output, the out boundary is the surface sigma that on which I have defined my PEPS tensor network. So in this situation, applying the Turaiff-Viro functor to my manifold will give me a linear map from the complex number to the state space of sigma. And that means if I apply that map, say, to the number 1 in C, I will get some distinguished vector in the state space. And what I want to show then is that the vector that I get is, in fact, the PEPS state that is obtained for the PEPS tensor A, which, remember, corresponds to the module constraint of this bimodule M. And once I know that this is the case, then explicit construction of the Turaiff-Viro functor here will in particular provide the construction of the protective subspace. And in order to make this going, I have to tell you first what the three-manifold M sigma is. I take just the cylinder over sigma. So this has 2 copies of sigma as a geometric boundary, but I take only 1 copy of them, say sigma tensor with 1, as what you usually take, what the boundaries here are about. That's also called the gluing boundary. That's where the microscopic degrees of freedom of my model are located. Whereas the other boundary at t equal to 0 I take to be a physical boundary where I specify boundary conditions. And that means that a manifold is of such a type. And then let's see what we can do in order to arrive at the situation that I want to have. So we first fix a skeleton for this three-manifold, which does not have vertices or edges on the gluing boundary. And for simplicity, just take this to be consist of prisms, which just are cylinders over the honeycomb lattice that I have on the physical boundary. And then I attach state sum variables to the plaquettes that I have in the interior. They are drawn in blue here, and they correspond to simple objects of D, whereas the plaquettes in the boundary, which is drawn in green, are labeled by simple objects of the module category. So if I look in a bit more detail, so that would mean labels A, B, C on these green hexagons, and alpha, beta, gamma on these faces here. Then to every edge in my skeleton, I associate a vector space. Edge consists of two half edges, and I define a vector space for a half edge just to be a morphism space that is defined by the labels of the three plaquettes which are to which it touches. So if I'm in the interior, all blue here, then I will have a morphism spaces in D. Whereas if I'm on the boundary, then I will have a morphism space in M. So for example, at this edge E1 here, I will have labels A and B from the green plaquettes, and then a label gamma from the blue plaquette here, and I will deal with this space here, and analog, and then I take the tensor product of this space with its dual, and then if I look at the whole three-manifold now with chosen skeleton, to that I associate the vector space, which I just get by taking the tensor products over all edges of these spaces that I have assigned to each individual edges. Now in these vector spaces, there are canonical vectors because they often form a vector space tensored with its dual. So I take an arbitrary basis in VE and take the dual basis in VE star, and then I take this particular vector here. And if I do this for all the edges in my skeleton, then I get a canonical vector in this vector space VP that is associated to my three-manifold with chosen skeleton. And then the next step is to define a suitable evaluation map. For this one uses the description of Touraev-Vero state sum theories as given in the book by Touraev and Viry-Lessier. And that works as follows. I look at an arbitrary vertex in P, draw a closed ball around it, like here, and then the intersection of the ball with the plaquettes will give rise to some lines on this on the surface sphere of this ball, together with vertices where they meet, and naturally each of the lines inherits an object label from the corresponding plaquette, and each of the vertices inherits vector space label from the relevant half edge. And then what I have obtained is a labeled graph on the sphere, and Turayef and Virilsley tell you how to evaluate such a graph. Essentially, this is again with the choice that I have made to use this particular P will be just evaluation of a tetrahedral graph, and evaluation of a tetrahedral graph will give you some type of 6J symbol. And indeed, by inspection, you see that the tetrahedral graph you get for this particular vertex is nothing but a PEPS tensor that we have seen before. And that means that the prescription for evaluation at this vertex is simply to associate to this the corresponding 3F symbol, up to some convenient normalizations actually. Now, if you now look what you're actually doing, then you see that you deal with a map from the tensor product over the vector spaces for all half edges incident to a given the vertex we are talking about, to the complex numbers. And if you then look at the vertex at the vector space for your whole 3-manifold, you can define an evaluation by the tensor product of all these evaluations. And what you get thereby is a map from the vector space to the tensor product of the vector spaces associated to the edges that are ending on the gluing boundary. That's because there are no vertices on the gluing boundary, so there is one half edge left for all those edges. And well, by construction, this is just the space H sigma. And now we have an evaluation map and we have defined a canonical vector. So the last step will be to evaluate this, to apply this evaluation map to the canonical vector. And what you see is just that in that you get precisely the PEPS description of the ground state that is associated to the fusion category D and module category M. And also by construction, of course, this is a vector in the state space of the topological field theory. So in particular, it lies in the protected space as it should. Let me briefly mention that you can also extend this to the situation where on your physical boundary you have additional Wilson lines. That means that you do not have just one module category, but you have different regions on your physical boundary labeled by, say, module categories M1 and M2. And then, so here this would be a region with M1. Here you have a region with M2. And you can show that the defect lines between two such regions correspond to objects in the category of D module functors from M1 to M2. And again, you can define then an evaluation map by the same prescription as before, except that now one of your lines is labeled by this new type of object. So you get a new type of graph, and it is not guaranteed that this is a graph that has already appeared in what I have been doing before. And indeed, there are two situations where you can directly use the results from before. Just take the situation that M1 is equal to M2, then the defect lines between M and M are just this functor category D, but this is a dual category, so it's C. And not surprisingly, what you find then is that the evaluation of the graph obtained in this situation gives you the MPO tensor, which is a 2F symbol. And another special case is that one of the two module categories is actually the tensor category D as a module over itself. Then the functor category can be naturally identified with the module category. In this case, you get a 3F symbol. And that's the end of my talk. Let me just tell you what one should also try. Of course, in the last situation, we should try to describe also what happens for arbitrary pairs of module categories M1 and M2. It turns out that when you want to do that, a useful tool is what is called module Eilenberg-Watts calculus, and you will hear a little bit about that probably in the next talk. Then, of course, one should describe the excitations. We have seen, well, these are the, what people call anions. These lie in the Drinfeld center of D, and then you should go back to the motivation and see whether with what I have told you actually you can do that stuff that that motivated you to look at these structures. Thank you.
Thank you very much for your talk. And some quick questions. Yeah, I guess as before, I guess you know the rules of applying now. I will just leave here for free discussion until the next talk at 16 o'clock European time, 4 p.m. European time, and also then we can discuss in more details in the at the end of the breakout sections. And you will have the third breakout section.
Okay.
Yeah, great. So now it's the fourth day. People are getting tired.
So,
Hi, Christoph.
hi, you can hear me.
Yeah, I can hear you.
Great.
I can hear you well. Yeah. So
Good.
you are a co-host now, and
Yeah, I have already shared the handout version, so that should be in the chat.
Okay, great. That sounds great.
And did you make me co-presenter?
I just made you the co-host.
Okay, good. Then
in case of your computer.
let me just see whether you can you now see my my PDF?
Oh yes, yes. You need to make it full screen.
There was recently some problem with the full screen mode. Can you see the full screen mode?
Oh, indeed. We cannot.
Yeah.
Oh, okay. So maybe. Yeah.
There's a workaround.
Yeah, we can do something like.
Let me just check this, and that's.
And these days, every single day, I have to delete certain files and restart my computer.
Yeah.
Every single day.
Can you now see the PDF?
Yes, yes. Now it's as good. Yes.
Then let me see. I can scroll.
Yes.
Yeah. Just that.
Exactly. Oh, that's very good.
Yes. Okay, then yeah. Good.
Yeah. So yeah, so these days I regret that I didn't update my computer before the
yeah.
before this wave that everyone needs to use their computer like twice as much every day.
Yeah.
Yeah, exactly.
Are you now in Göttingen?
I'm now in Göttingen, right? So yeah. So I don't I actually didn't go out of Göttingen since February. Yeah,
Yeah, that's a long time.
That's a long time. Yeah, so I dare not to go.
You must know many details of Göttingen by now.
Well, maybe I know a lot of details of my apartment by now.
Okay, but you could leave the apartment, I guess.
Yeah, yeah, definitely, I can leave my apartment. Yeah, exactly. So what is yeah, so what is even more funny is that like at the end of the semester I got a lot of coughing because of something I don't know. I didn't even leave my apartment. I got really horrified. And my house ex also got horrified, and he or she asked me to test, and it was negative, so I can make a turning with her. And it turns out it was certain allergy. So
yeah,
it was maybe I eat something too spicy.
Yeah, these are strange times.
Yeah. Then maybe, yeah, she told me like everyone who has like a coughing or cold signals, at least now here in Göttingen, you need to make a test first, then she give you a tummy, and she actually helped you to make a test.
Okay.
So and I guess that sounds also, yeah, for the rest of people maybe it's safer. Now I went through it. So let's see there, like still a couple of minutes. And,
yes, 3 minutes or so.
Yeah. So when did you begin to work in topological order related things?
Well, it depends how you define topological order. Of course, you can define it by now in such a way that we all started, well, decades ago. I mean, the project Jürgen was talking about was something we initiated last year when we visited Ghent.
Mm-hmm.
So that was a very fruitful visit.
I see. Yeah, I see this now, and yes, it definitely seems as though the next wave of next wave for people working on high category and math physics.
Yeah. And it's probably closer to physics than some other applications of high categories, of higher categories.
Definitely. What I find really really nice is that finally something well, I might say something wrong because I'm not a physicist, but finally something that which is measurable in reality could might be there related to our very abstract calculation. So that sounds really exciting. So time is approaching, and the next talk will be given by Christoph Schweigert from Hamburg, and he will talk about bulk fields in conformal field theory. Thank you, Christoph.
Yeah. Okay, thank you very much. And let me first recall one thing we've learned in Professor Wenn's lectures. He said that we have to learn category theory because it is really a very natural language. And what I want to show you is that category theory and really basic notions of category theory are the correct thing to address rather intricate objects, namely bulk fields in two-dimensional conformal field theory. Now, two-dimensional conformal field theory and fusion categories or modular categories, that's a very well-known connection. It appeared a little bit in Yasu's talk. So let's go back and look at a little bit of history to start with. So if you want to determine bulk fields, then it has been clear, at least since the 80s, work of Belavin, Polyakov, and Samologikov, but also many others, that you have to solve associativity constraints. So you have to look for certain algebras. Then these algebras have been attempted in the 80s and the 90s to classify them based on the modular data, so on the S matrix and on the T matrix. And in nice cases, this has led to ADE classification, but in the mid-90s, it was clear that classifying modular partition functions is really not the good thing to do, because quite a few of the modular invariant partition functions are definitely unphysical, and even worse, it's very difficult to detect whether a modular invariant partition function is physical or not. Well, then in the 2000s, it became more and more clear that in the semi-simple case, you can construct a full local rational conformal field theory in which left movers and right movers are combined from the additional datum of a module category over it. In fact, a rather specific one, a semi-simple module category that is indecomposable, or alternatively by prescribing certain symmetric Frobenius algebra. Well, in this talk, and this is probably the first talk in our workshop, it will be important that I will not insist in semi-simplicity. So I will use the power of category theory, which is already incredibly useful in the semi-simple case, to extend all these constructions beyond semi-simplicity. Of course, I have to keep something to have a well-defined mathematical framework, and what I will keep are still certain finiteness properties. So what is my plan for today? I want to take you on a big tour And I will start in a field of pure mathematics. I will talk about some things in classical representation theory of finite dimensional algebras, and you don't lose anything imagining finite dimensional algebras over the field of complex numbers. And there will be nothing like Hopf algebras or categories with a tensor product like fusion categories or their non-semi-simple cousins. Only in the next part, I will go to monoidal categories and module categories over them and develop tools which in the end will give me a very compact description of bulk fields in two-dimensional conformal field theories beyond the semi-simple case, beyond rational CFTs, if you incorporate the word semi-simple in the word rational. So the next part of the talk is in principle in pure math. It is about representation theory of finite dimensional representations of a finite dimensional algebras, and it is some very classical stuff. So take a field, the complex numbers is fully enough, and then we look at a class of categories which I could informally describe as a category that is equivalent to the category of finite dimensional modules over a finite dimensional algebra. And for these categories, there is some intrinsic characterization. So there are nice finiteness properties. So every object has a finite length, there are enough projectives, and there are finitely many isomorphism classes of simple objects, but we do not require that that any object is a direct sum of simples. And a finite tensor category is then, that's what we are going to use a bit later, is a finite category that is monoidal and moreover is rigid. So we have left duals and right duals that will enter quite crucially at the technical level. For example, the tensor product functors in our context will be always exact. Okay, so now there's a classical fact of algebra which dates back to the 1960s, and it's the following thing. Suppose we have two of these categories, A mod and B mod, and we want to describe functors. Well, in this situation, you shouldn't look at all functors, but at right exact functors. So, now any of such a right exact functor, so this shouldn't be tensor, this should be functor, can be written by tensoring in the form of tensoring with some bimodules. So right exact functors are all of the form tensoring with some bimodule, and the bimodule can be obtained pretty explicitly in terms of the algebra A and the functor. And there will be a complete symmetry in this first part of the talk between right exact and left exact functors. And there's a similar expression of getting left exact functors in terms of bimodules using not a tensor product, but a Hom. Well, okay. So this is a nice classical result, but it's not terribly useful for conformal field theory because typically, we want to discuss things in categories of representation, say over vertex algebras, and not over some finite dimensional complex algebras. And then we have just a categorical word, but not a very explicit algebraic word. So it's much easier to work than in the categorical word. Okay, now the first part, I want to explain to you how to phrase this Eilenberg-Watts theorem in a categorical way. And what I want to do is I want to relate left exact functors, right exact functors, and bimodules. And these bimodules, they are described in terms of this product of tensor categories, in terms of the so-called the linear product of tensor categories. Well, the linear product of A mod and B mod is A tensor B mod. It can be characterized by some universal property as any decent tensor product should be. And before explaining what is functors here, psi L and phi L, phi R and psi R are, they will be adjoint equivalences. Let me look at some tool we will need a lot in the sequel. So I need co-ends and their dual version ends. So for the physicist part of the audience, we are all used to implement something like sum over states. And if you think about state sum models, as we have seen them in Jürgen's talk, in the semi-simple world, you would sum over all irreducible representations. Well, not all irreducible representations, but all irreducible representations up to isomorphism. What is the coend? Well, informally speaking, the coend is a sum over all representations up to all morphisms. And this is a notion that makes a lot of sense even beyond finite semi-simplicity. So what we do is we take the sum over all objects. For example, if I want to take the coend of X dual tensor X, that's of course a huge object, and we mod out, roughly speaking, all morphisms, and this is defined as a quotient. What you should keep in mind is that a coend is a variant of a direct sum, and we teach our students in the first year in linear algebra that morphisms out of a direct sum are characterized, are the same as families of maps into the direct sum. And of course, families of maps. And there's a fundamental thing in category theory, which is you can reverse arrows. If you reverse arrows, then you get a sub-object of a product. And a sub-object of a product that is defined in an analogous way is called an end. And the integral notation is standard in the mathematics literature. It is very well justified. For example, there is a Fubini theorem for ends and for coends. Well, you have all seen ends and coends. For example, the trace is just a coend. So if you take the trace in the category of, say, finite dimensional vector spaces over a field K, then this must be a vector space. Well, there are not so many distinguished vector spaces. So this is the vector space, which is the ground field itself, and it must come with a morphism as the direct sum does. This is a morphism from V tensor V dual. So these are endomorphisms of V to K, and this is the trace. And all the properties of the coend, the universal properties, are things you learn in a more elementary language when discussing properties of the trace. What's also quite important is that you can write natural transformations of between two functors in terms of an end. Indeed, an end is a subspace of a product. A natural transformation is characterized by its component. So it has many components in a product, and they obey certain relations which single out a subspace, and that's what the end is. And so this formula of natural transformation is something I would write to a blackboard in Vienna and leave it for the rest of the talk. But here we don't have blackboards, but you have the transparencies as a PDF file. So please keep this formula here in mind. Well, now I said that the end or the coend behaves very much like an integral. An integral should have something like a delta function. And indeed, the Hom behaves like a delta function. So if I take any functor g and any linear functor, and I tensor it here with Hom, then I get back the functor. So that's a decomposition of the functor in terms of a coend. And the Hom is something like a delta function. Now, our Hom spaces have been finite. That was a finiteness condition I was highlighting. So it is innocent to take the dual of as a vector space. And that's what I take here. And then you get a similar construction of for the end, that the dual of a Hom space behaves like a delta function for the end. And indeed, in this talk, and very importantly for bulk fields, we have to be aware of the fact that the Hom has some relative, which is the dual of a Hom. Okay. And to give you some usefulness of these notions, maybe most of you are probably familiar with the Peter-Weyl theorem, which expresses the space of functions on a Lie group, say, in terms of irreducible representations. Well, in terms of the end or the co-end, you can write down a Peter-Weyl theorem also for finite dimensional algebras that are not necessarily semi-simple. In this case, of course, you cannot expect that A as a bimodule can be written as a direct sum of simples, but the end, or for a dual, the co-end, give a very good expression that can be easily manipulated. And that's what we are going to manipulate in a moment. So I want to explain this Eilenberg-Watts calculus. So I want to relate left exact functors, right exact functors, and here, this is my categorical replacement of bimodules. An A module, well, the opposite actually of it, tends with B, so the opposite here turns left modules into right modules. Now, how do these equivalences look like? Well, let me just flash the equivalences. They involve, for the left exact functor, the Hom, which famously is left exact. For the right exact functor, the dual of the Hom, that's something you should keep in mind. And then the inverses are defined using essentially this Yoneda version of the Yoneda lemma in terms of co-ends and of ends. Now, look at this diagram and imagine for the moment that A is equal to B. Then we have endofunctors. Endofunctors can be composed, so this is a monoidal category. And there is a distinguished endofunctor, which is the identity. It is quite important that if you go from the identity as a left exact functor, you turn it into a bimodule, and you turn the bimodule into a right exact functor, you don't get the identity as a right exact functor, but you get a functor, a right exact functor that's very famous in representation theory. And indeed, what you get is this functor here, which is called the Nakayama functor. It is defined here in this, in terms of this co-end over the dual of a Hom. And of course, there's a dual definition, which gives a left exact functor. And if you compute what it is in case of the representation category of an algebra, it is the classical Nakayama functor you can find in textbooks. So you investigate these functors, you see that they are adjoint. You can study the case when they are actually equivalences of categories. And what's quite important for our talk is that if the Nakayama functor is trivial, and if A is the category of modules over an algebra, then indeed this algebra comes with the structure of a symmetric Frobenius algebra. So we have a categorical way of talking about symmetric Frobenius algebras. This is one thing. Now, for bulk fields, I need one more observation, namely, sorry, this, if you take here the image of the identity functor is the left exact functor, you can write it as a co-end, but using the right exact part of the Eilenberg-Watts calculus, you can also write it as an end. It's an end, and there is a twist here by the right exact Nakayama functor. But the important thing is that we relate an end and a co-end. So very roughly speaking, something like a direct sum and a product. And that will be important to get co-multiplications and multiplications on bulk fields in a moment. Okay, so now this was the first part. So far, I should emphasize no monoidal categories, no Hopf algebras, everything in the realm of finite abelian categories or finite dimensional algebras and their finite dimensional representations. So I have now to introduce some additional structure, and this is the following thing. The notions were already mentioned a couple of times. So a monoidal category is something like a monoid in categories. So you have a tensor product. And if you study monoids or algebras, you want to study modules over them. So module categories are categories together with a mixed tensor product. which allows you to act with an object of the monoidal category on an object in the module category. And of course, you can also act on morphisms. And already in Jürgen's talk, well, there are left module categories, right module categories, bimodule categories, and then you can define module functors, module natural transformations in a rather obvious way. A very important example that will be related to the Cardi case in CFT is the case when that any monoidal category is module category over itself. In fact, a left module category, a right module category, and a bimodule category. What we will use is that it is a left module category over itself. Okay, the module categories I'm going to consider are finite module categories, but they are not necessarily semi-simple. And so they have, again, finitely many simple objects, but not necessary. It's not necessarily true that any object is a finite direct sum of simples. And the action obeys several nice properties. Now, a very important notion we need from category theory to understand these bulk fields is the notion of an internal hom. So if I have a module category, then M is a module category, then the internal hom is an object in the monoidal category. And it is an object in the monoidal category that is defined by saying that the homs from any C into the internal hom is given by this space of homs in the module category. So this is a way to obtain objects in the monoidal category, and in fact, much more than objects. It turns out that these internal homs can behave very much like objects you know. So for example, let's take the monoidal category of super vector spaces. So these are Z2 graded vector spaces with a certain braiding. The homs, the ordinary homs in the category theoretic sense, are grade preserving linear maps, but the internal homs are themselves super vector spaces. So these are matrices that have even components and odd components, and everybody who has calculated with some superstructure has implicitly used internal homs in this category of super vector spaces. And what is important is very much as you can compose homs, you can compose internal homs, and they are associative. The composition is associative, of course, associative with respect to the associator of the monoidal category C, because the internal hom is an object in the monoidal category C. Okay. So now this is a technical slide, but it will be quite important. I've explained to you in this section where there was no monoidal category, and this is in principle a proposition that belongs to this section, that the Nakayama can be seen as kind of a relative of the identity functor. The identity functor famously commutes with any functor f. The Nakayama functor, because also the composition is changed, doesn't commute, but if you commute it, you have to take a twofold left adjoint. And of course, you have to assume that the twofold left adjoint exists. And then you can see that if you're commuting any functor past a Nakayama functor, it gets a twofold left adjoint. And actually, this is a famous, leads to a famous generalization of a famous result in Hopf algebras, namely the Nakayama functor. If I'm looking at a bimodule category, well, the Nakayama functor on a bimodule category, I can act with an object of A on the left or with an object of B on the right. And if I pull it right out of the Nakayama functor, I get biduals. This is actually the left adjoints I have here, and it follows from this theorem. And then it's a rather straightforward calculation, which I probably won't go into too much detail, to show that if you specify to this case, which I mentioned earlier, namely that the finite tensor category is a bimodule over itself, that then if you notice that this the value of the Nakayama functor, the monoidal unit, is the distinguished invertible object, the one that classifies integrals of a Hopf algebra, then computing this in two different ways and using that A is equal to A tensor 1, you see that these two expressions are equal, and you recover that conjugating with this distinguished object gives a fourfold dual. That's, of course, the categorical version of Redford's S to the fourth theorem. Now, why is this important? We're going to use this in a moment. Now, I want to define Serre functors. So I define it in the following setting. I take a module category over a monoidal category, and then I want to relate Homs, duals of Homs and Homs. That's how you define a Serre functor. Now you can say an ordinary Serre functor, well, there is no inner Hom. You just take the ordinary Homs, and this is in standard algebra not a very interesting notion, because Serre functors exist only if the algebra is semi-simple, and if you want to have Serre functors in more general settings, you have to go to derived settings. Here, I'm not comparing Homs, but I'm rather comparing inner Homs, and then it turns out that such Serre functors exist. Such Serre functors exist for a famous class of module categories, so-called exact module categories. They have an intrinsic characterization. They have been classified, for example, if you realize module categories in terms of module algebras over a Hopf algebra. And you can show that Serre functors are equivalences of categories, and they are twisted module functors. Twisted module functors means that they, if you have an action by an object in a monoidal category and it travels out of S, it gets twisted by a bidual, a right bidual or a left bidual. And actually the Serre functors are closely related to the Nakayama functors. So, well, they are twisted module functors, and now there's an important thing. Trivialize Serre functors. That's something that probably anybody who has seen some advanced course on algebraic geometry has come across. So what do we mean here? Well, we have, if we want to trivialize, we want to say the Serre functor is the identity functor, but it's a twisted module functor, and the identity functor is not a twisted module functor. So this only makes sense if we can trivialize the bidual. And this is what one calls a pivotal tensor category, in which the object and its bidual can be identified, and that's structure. And then a trivialization of the Serre functor is called the pivotal structure. That's essentially trivializing the Serre functor as a twisted module functor relative to the pivotal structure of the monoidal category. Okay. It should be emphasized that for the monoidal category, the pivotal structure is structure. For an indecomposable exact module category, by some Schur's lemma type argument, it is essentially unique. It is unique up to the scalar. So it is a property. Okay, this is what I need to discuss bulk fields in two-dimensional local conformal field theories. And the setting I'm now going to is finite categories with more structure. Still, they are not necessarily semi-simple. They are finite in the sense I've defined. They are braided, and the braiding is non-degenerate. So there's one property that which also appeared in Wen's talk, that the Müger center is trivial. There are other characterizations of a non-degenerate braiding. For example, that the Trinfeld center can be written, is braided equivalent to C, the linear C with the opposite braiding. And all these characterizations of a non-degeneracy of the braiding are known to be equivalent. And it is known that categories of suitable vertex algebras lead to modular tensor categories. And there are also a couple of more sources. In any case, think about this modular tensor category as axiomatizing the chiral data, the Moore-Seiberg data of a conformal field theory, a chiral conformal field theory that is not necessarily semi-simple, but still has finiteness properties. Of course, the semi-simple case is contained here. That's a special case. Now, what do we know about fields? Well, fields in a two-dimensional conformal field theory, they should transform in representations of the chiral algebra, so they should correspond to an object in our category, and they should be obtained in the case of bulk fields by combining left movers and right movers, so they will be ultimately objects in the Drinfeld center, and they are OPEs. So they should be, the OPE gives them an algebra structure and even a bit more a Frobenius algebra structure. And the pictures I've stolen here, they are from Llewellyn's 92 paper. And the modern way to express it is to say that the bulk fields should form a Frobenius structure, and the boundary fields should also form a Frobenius algebra, a symmetric Frobenius algebra. So how do we get them? Starting from a finite modular tensor category plus some additional datum. Well, the additional datum, and that's essentially what we learned in the 2000s, is a module category, a suitable module category over the modular tensor category. So the interpretation of this module category is that the boundary conditions are objects of this module category, and the boundary fields, which can change a boundary condition M, object in calligraphic M, to a boundary condition N, they are given by inner Homs. Inner Homs are objects in C, so no left movers and right movers combined, that's okay. And the OPE, which should be associative, is just the composition of inner Homs. But remember that we should get not just an algebra, but a Frobenius algebra. So for this reason, we require M to be a pivotal module category, because there is a proposition which states that if you look at a pivotal module category, then the inner Hom, or the inner end, to be more concrete, is not just an algebra by composition, but it has a Frobenius algebra structure. This is something which developed in several steps, and it's most notably related to the work of Schaumann and of Shimizu. So, it is therefore clear that we can get a good theory if we go to pivotal module categories. So module categories which admit a Serre functor, in which the Serre functor, which is essentially up to a scalar property, can be trivialized. So now, what do we need to do? We have to take a pivotal module category and we have to extract from this an algebra describing bulk fields. And this is an algebra which combines left movers and right movers. And due to the fact that this is a modular tensor category, it should be an algebra in the Drinfeld center. So we should obtain a Frobenius algebra from the boundary data, and we should get this not only for the bulk fields, but there are many more fields in a conformal field theory. There are defect fields and disorder fields, and we should get algebras for all of them. So let me explain how this goes. Now, the situation is now, the most general situation is now the following one. We fix the chiral data once and for all, and they are described by a finite modular tensor category. So this includes certain types of logarithmic conformal field theories. Now, how to combine left movers and right movers, that's described by M1, which is a pivotal module category over C. But there can be different pivotal module categories, and you can consider local CFTs labeled by different pivotal module categories and that are separated by a topological defect. Well, such a defect needs labels, and it is a very obvious idea to choose as labels right exact module functors. So we have here a defect of type F, which is a right exact module functor from M1 to M2, a defect of type G, which is another module functor, and we need to produce from these data some object in the Trinfeld center, which has the property that, for example, if F is equal to G, we get a Frobenius algebra. Now, how to do this? Well, maybe we first look at this picture. If we take the Poincaré dual of it, you get something which looks pretty much like the standard picture you see in category theory to describe natural transformations. So probably the thing we are going to do should be related to natural transformations of functors between module categories. So they should be related in some way to module natural transformations. Well, actually, let's start a discussion from a slightly different point of view and come back to this picture in a moment. Yeah, let's note that this category of right exact module functors is itself a module functor. It is a module functor. Well, you could try to turn it into a module functor over C by simply acting with C on the result of applying a module functor F on M1, but then it's not a module functor. You need some more structure to get the structure of a module functor in it, and that's precisely a half braiding. So these functors are actually, in a natural way, a module over the Trinfeld center. And the Trinfeld centers, or a pivotal category, is itself pivotal, and we will always take it with this pivotal structure. So what do we want to take? We want to now consider internal homes over of this module category Rex over the Trinfeld center. And let's investigate this. Well, the following formula is incredibly useful. In the beginning, I said there was a formula that I would have written on a blackboard in Vienna, and that would have stayed for the whole talk. And this formula was a formula for the natural transformation between two functors. And so take this formula here without the underscore, forget about this in the Trinfeld center, and we would have taken the end of Homs. Now what we do is we can show that this object not in Fg is actually, well, it is an equal to also an end, but an end where the ordinary homes are replaced by inner homes. And yeah, so this is the formula for the natural transformations. And if you modify it, you get a natural source of interesting objects in the Trinfeld center. And let's first go a little bit back to the case where of ordinary natural transformations. If you do it for a category of modules over an algebra, then the natural transformations from the identity functor to itself are the Morita invariant way of expressing the center. And so this here is an expression for the center of an algebra. What you see is that if we put F and G equal to the identity functor, this would be a transparent defect. Then we get something like an internalized center, and that's the bulk algebra. Now, this really behaves like natural transformations. Natural transformations can be composed vertically, but they can also compose horizontally. And the same is true here. And they obey the relations you expect for natural transformations. In particular, you can apply an Ekman-Hilton argument, and this Ekman-Hilton argument implies that this, or rather an analogous thing for the bulk algebra, is not only an algebra, but it is a commutative algebra. So we get a nice source of algebra. For conformal field theories rather than algebras, we want to have Frobenius algebras. So let's see how to get Frobenius algebras. Now, there is a variant of this Eilenberg-Watts calculus, which uses which doesn't apply to functors, left exact functors or right exact functors, but to right exact and left exact module functors. And then you have to take here a category which is the linear product plus some balancing. Well, if you go through this diagram, you get again a relation that identifies an end and a co-end. So that here we have a source to get a relation between ends and co-ends. Co-ends famously want to be co-algebras, ends want to be algebras. We can identify them. So this is already half a way to go to Frobenius algebra. More complicated, and these are the recent theorems which prove what I just informally tried to announce. So suppose we have a pivotal finite tensor category, and if C is modular, then it has a distinguished pivotal structure. And M and N are exact for C. The category is an exact module category, and one can compute its relative Serre functor. And the relative Serre functor can be expressed in terms of the relative Serre functors of N and M, and distinguished object for the monoidal category C. Now, the distinguished object is not so important if you're interested in modular tensor categories, because in this case, D is isomorphic to the monoidal unit. Now, the second thing you can show is that if this is unimodular, which is true for modular tensor categories, and if M and N are not only exact, but pivotal, so if they have trivial Serre functors, then also the right exact module functors are a pivotal module category over Z of C. And now we can invoke Shimizu's general theorem, which says that if we take inner ends in a pivotal module category, then these are not just algebras, but they have the additional structure of Frobenius algebras. And in the case of the special case when F is the identity functor, then we have a commutative symmetric Frobenius algebra. And the fact that I'm saying commutative symmetric is not doubling things, but in the braided setting, one has to say the two words. So these are very good candidate for bulk fields, as I want to explain on the last slide. Before explaining this, let me mention that if you apply it to the case where C is semi-simple, then a pivotal module category is necessarily semi-simple. You can compute, for example, what these internal natural transformations are, and you will find formulas for this object, which are exactly the one for bulk objects that have been derived in the TFT approach to RCFT correlators almost 20 years ago. But here, no mentioning of semi-simplicity. This works for logarithmic CFTs as well. And once you get used to these categorical tools, also the construction, in my opinion, becomes more transparent. Okay, so now let's go back to the 92 paper of Llewellyn. So this is, all these drawings are stolen from Llewellyn's paper. Well, Llewellyn says that if you want to construct open-closed correlators, and he has a single boundary condition, but that's a minor detail, you have 3 building blocks. So that's the way he phrases them. Well, this here is the product for the bulk fields, but of course we can read it this way and this way. So it's a product and a co-product, and they have a Frobenius algebra structure. Then you have a similar thing for the boundary fields. That's also a Frobenius algebra, because we have them realized them as inner homes of a pivotal module category. And then there is an amplitude which allows you to go from a boundary field to a bulk field. Now, in our situation, we have natural transformations which are characterized as an end. As a consequence, we have really structure morphisms of an end, which give us something like components of a natural transformation. And so we have morphisms which go from the bulk field to hom MM, which would be boundary fields that do not change the boundary condition M, but transform it into the boundary condition M itself. So we have this natural candidate for this building block in Llewellyn's paper. First, since it's an end and a co-end, we have also arrows in the other direction. So now in Llewellyn's paper, you also find these consistency conditions. Here, A was already on a slide. That's the fact that bulk fields are Frobenius algebra. That's now for this formula for the bulk fields, that's a theorem. C means that the boundary fields are Frobenius algebra. Now, let's look at the other things. So what do we have? We have, for example, E, and then you see that here you first take the component maps and then you multiply open strings or boundary fields. And here you multiply bulk fields and then you take the component map. But that's quite easy to understand because the vertical composition of natural transformations is defined component-wise. And it turns out that this holds for these internalized natural transformations as well. So E is kind of very automatic. And the same applies also to D. If you see here, you have boundary condition A and B, and their role is exchanged. And actually, that's a consequence of the fact that our end or co-end enjoy dinaturality properties. Admittedly, B and B and the last thing, F, so-called Cardi constraint, they are more complicated. They don't follow from what I said. That's still an open problem. And you see here that these are genus 1 constraints. They are much more complicated to deal with. That's almost already the first comment in the outlook. Of course, one of the things you want to do with this very nice algebraic structure is you want to describe then correlators and use modular functors with various formulations of modular functors, state some string nets. We have formulations of modular functors for Reshetikhin derived type, and even their non-semi-simple variants due to Lubachenko. And all this can be used to explore then correlators. And of course, rigidity was technically important here, but for CFT, interesting cases without rigidity for the chiral data, and the formalism should be extended to them as well. So this was essentially what I wanted to tell you. Thank you very much.
Thank you. Oops. Oh, thank you very much, Christoph. And let me just mention that maybe there are some questions, but immediately will be our question section in like for 1 hour. So I hope you can hold your question a little bit, or unless there's some urgent ones. Okay, good. So let me just remind you that today the discussion section 1 doesn't work, but 2, 3, 4 works. So 2 for Yatu, 3 for Jürgen, and 4, and the 4th one for Christoph. And you will come.
Cheng Cheng?
Yeah.
Yeah, may I make a suggestion?
Sure.
Since I'm also involved in the work Jürgen was presenting, it would make some, and Jürgen is involved in the work I was presenting, it would make some sense to combine our discussion section.
Okay, great. So,
Yeah. So if you don't mind, I would go to 3 as well.
Okay, great. So let's say 2nd is for Yatu and 3 is for Christoph and Jürgen, the 2. And please, and I think you all have the links and you just go there. And for people who missed the talks are in YouTube. And I get the really organized one, like cutting to each speaker and polished one, will be in ESI's homepage later on. But if you just want to watch the YouTube like without polishing, it's on this website, right? So you can just click on YouTube and get your link. For example, I do it, copy stream link, and I copy, I paste, and it's over here. So you can review the sections in YouTube. And also I will actually put such links in, I think in the schedule, yes, in the schedule title abstract documents on our website in ESI. So you go to ESI, there's a blue link saying schedule title abstract, and you click on that, and each day's YouTube link is over there. So non-polished one is over there. Are there like more organization questions? Okay, if not, tomorrow is like 1 o'clock European time, 1 p.m. European time. And so there is there is such a change, and every day we start at a different time. It's such a challenge for our memory. So tomorrow is 1 o'clock, and otherwise our section will be closed soon, and you should go to section 2 and section 3 for deeper discussions with the speaker. Okay, great. More questions? No more questions. I end the section 2. Section 2. Okay. See you.